differential equations. So it's here. The content of today's topic is limit and continuity to begin with, differentiation, successive differentiation, mean value theorems, Taylor's and Maclaurin series, integration, definite integral, double and triple integral, differential equations. We deal with linear homogeneous ODE, linear non-homogeneous ODE, Cauchy-Euler, and linear PDE. And then we go back to numerical methods, wherein today we'll deal with integration and ordinary differential equation solutions. We'll discuss Euler's and Euler's modified, Runge-Kutta 4M. Adams and Milne is an extension of Runge-Kutta 4M in the sense that we use the formula Runge-Kutta 4M or Euler's modified and predictor corrector so that we get the next three possible values and then use them and then just write the formula. So it's not very difficult. We need to just write the formula and then get Adams predictor and corrector, and similarly Milne's predictor and corrector. That should be simple. Then we go to integration. We'll discuss the trapezoidal rule, Simpson's rule, and Romberg integration. So let me begin my presentation by opening the spider. So as usual, spider is here. I'll open some differential characters things today. MST3. So continuity and differentiation. Okay. So today we all know what continuity is. Now there is no break in the curve, then the function is said to be continuous in the entire domain. So suppose if a continuity at a point is discussed in terms of limit of the function, the left hand limit and right hand limit should be equal to the value of the function at that particular point, then the function is said to be continuous. So limits can be found out very easily using SymPy in Python. So from SymPy we import the symbol, then some functions and also a limit here, exponential function, sine function, tan function for to begin with, then limit. So we give x is equal to symbol x, y is equal to symbol y, h is equal to symbol h, as usual, which we learned yesterday also. So to discuss continuity, we take some y is equal to tan e power x or y is equal to 1 by x or whatever. And then we give, substitute x is equal to 0 plus h and evaluate f. So that means the value of x will be taken as h and y is equal to 1 by x means 1 by h it will take. Similarly, substitute by x is equal to 0 minus h and evaluate f. So it will take minus 1 by h. Then find the limit of q1, h at 0. So you know that if at h goes to 0, you get minus infinity and plus infinity. So at 0, it should not be continuous. So let us check what happens here. Print w1, w2. So if it is continuous, then if it is differentiable, then this is printed. So let me stop only the sorry. So I'll comment this. Now, as we mentioned, limit, if it has to be evaluated, then the do it command has to be given. And finally, the function value is evaluated by substituting x is equal to 0. Now we need to check whether w1 and w2 are equal, and w1 w2 must be equal to y1 also. So only then it is continuous. So let me run the program. So you're getting infinity and minus infinity. So OO and minus OO. So is it continuous? I don't think it is continuous at 0. So we give some other value. Instead of 0, we can give, or we can take the other function. We can take the other function here. Y is equal to tan e power x. Y is equal to tan e power x. Suppose we run this, you are supposed to get tan 1 and tan 1. Okay. Tan 1 and tan 1. So suppose if this is true, then left hand derivative should be equal to right hand derivative. So it has printed w1, w2, and also y1 it has to print. So let me see what y1 it will print. And again we'll comment. Run the program. y1 it is printed as 1.55740, which should be equal to tan 1. Now if we give, it will not give tan 1, so it will not give equal, because tan 1 it will take it separately as 1.557. So we need to give eval f. So do it, and then we have to give eval f. So let me do that, right? Or I can do it if we give it to work. So print w1 dot do it.
Madhukar sir,
Yes, sir.
someone has presented in between.
Okay. 1 minute.
Need to present.
Yeah, I will log in. Yeah. Thank you, sir. So w1 dot do it. If we do, I think it should come. So let me check. No, it has not taken tan one or just two. So the reason is because it takes it as a string value, and then you need to convert it into float or something. So that is float of. Okay, 1 minute. Float of w1 suppose I do. And this. Yeah, now we got 1.55740772. Now if we give, if w1 is equal to w2, and also we can give the logical operations, and float of w1, because we know we have to convert it, is equal to y1. Then print y is continuous. Comment it here. Yeah, so tan e power x is continuous. At the point x is equal to 0, we have to give, which is understood. Then we find out the derivative. Z1 is equal to limit f of x plus h minus f of x divided by h, f of x minus f of x minus h divided by h. So both are evaluated, and if this is equal, then it will show that it is differentiable. Obviously, it should be differentiable. Tan e power x is differentiable. Tan e power x is minus infinity and infinity at 0. Tan e power x is continuous. Q2, Q2, suppose we get, and we are supposed to get minus h here because it is f of x minus f of x minus h. So f of x minus h, f of x minus f of x minus h. So minus h, f of x minus f of x minus h divided by x minus h. Get this. The first one is f of x plus h. The limit is h tending to 0. So x minus h tends to x. So minus h tends to 0. This should be. Let us check this. It has to show that it is differentiable at 0. Tan 1. Tan e power x, tan e power 0 is tan 1. So it should be differentiable. We'll take up the next example. Probably we take up a better example than this, which is much simpler. E power x itself. Let us say e power x square. Suppose, when we do the entire thing for that, it should be differentiable. So let us see. Yeah, e power x square. So it is very simple. Just like doing our usual mathematics, we can do this for using Python. Next, we'll go to L'Hopital's rule, or finding out limit using for indeterminate form. So here I have taken the expression e power x minus 1 divided by sine 5x at x at 0 So do it if we give, then print L. Similarly, 1 plus 1 by 5x whole power x. So this is of the form f of x whole power g of x. So whether this is this is an indeterminate form, infinity by infinity. So we need to find out whether it is 0 power infinity. So we need to find out whether the limit is evaluated or not. Obviously, the limit gets evaluated. So we know that the first one should give you 1 by 5. The second one should give you 1 plus 0. So it gives you e power 0. E power 0 is 1. So you get 0, 1 here. For any function you can try out. We'll go to the next session, next concept of we discussed continuity and differentiability. Then we discussed L'Hopital's rule. Then we'll go to mean value theorem. Say probably we can take up Rolle's theorem. Obviously, we know what Rolle's theorem is. We know that if f of a is equal to f of b and we have continuous function in the closed interval a comma b and differentiable function in the open interval a comma b, then there exists a point C such that f dash of C is equal to 0. So we need to find out that particular point here. So we have taken the function, a polynomial function is always continuous. So 2 minus 9x, it is differentiable also. We find the derivative of it, dy. Then we substitute 0 and 3. So q1 is equal to y dot subs x is equal to 0 and y dot subs x is equal to 3. Then print q1, q2. So you know the value it should give you. Now if it is equal to 0, Rolle's theorem is valid and we need to find out whether it is valid or not. So we need to solve, we need to find out q in such a way that q lies between 0 and 3. Let us see whether q lies between 0 and 3. It should come as 1.5 probably. Now minus square root of 3 is the mean value. Minus root 3 and square root of 3. Square root of 3 is 1.732. So it lies between, one of the value lies between 0 and 3. So the mean value theorem is valid. So we can give a statement here if q1 is equal to q2 and so okay. Okay. So we can give q dot solve dy outside and we can print q1 and q2. Q1 and q2 we got it as 0 0. So the three conditions are valid. Now if q1 is equal to q2 and q is less than or equal to 3 and q is greater than or equal to 0, then print at q is equal to q and is the mean value. Let us check whether this happens or not. Because there are two values, I think I have to give q of 1 or q of 2 or something like that. We'll see whether it comes out to be. So I don't think it comes. So we need to give q of 1. Q of 1 is less than or equal to 3 and q of 2 is less than or equal to 3 and sorry, we give this condition or we can give here or q of 2 is less than or equal to 3 and q of 2 is greater than or equal to 0, then you can print this. So we can close the bracket. The next bracket is closed here, the next bracket is closed. So let me check whether this works or not. This object is not callable because it prints as string, that is list. So this object is not callable. Okay, so we need to convert it into float, then float value should be taken and so on. So it is a tedious process, but we can do it. There's no impossibility there. So we'll go to mean value theorem, Lagrange mean value theorem. The concept is same. Only thing is f of b minus f of a divided by b minus a. So whether this is verified or not, we can check. So here you see, yeah. So LM minus 2.645 is the mean value, or 2.645 is the mean value. It lies between 1 and 4. 2.645 lies between 1 and 4. The function again is x cube minus 9x minus 3. Then extension of mean value theorem is Maclaurin's and Taylor's series. I have done two Maclaurin series, so we can take up Maclaurin's sign here. So we know the sign function x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial and so on. So here we declare a function Maclaurin sign value comma k, where how many values we need, because it cannot go up to infinity obviously. So therefore the first value is taken. First value is x. So x is pi by 180 into the value. Then it is 1 comma k and plus or minus. So 2 power 2k plus 1. So therefore, if you compute this, so you get 1.00002, which is for 90 degrees. Sin 90 is 1, we know. Sin 45 is 1 by root 2. 1 by root 2 is 0.7071 something. Then sin 30 is half. Half is approximately calculated here as 0.4999, etc. 4. So this is also for the same value, but I don't think this is correct. So we'll deal with only the first one. Okay, so maxima and minimum problem we can discuss. So we know that suppose we have a function with respect to x and y, then the maxima and minima can be found out using del square f of x dou square f by dou x square into dou square f by dou y square minus uh, dou square x f by dou x dou y the whole square, dou square f by dou x dou y the whole square. So here I have considered the function x square plus xy plus y square plus 3x minus 3y plus 4. Then the derivative with respect to x, perform it. Derivative with respect to y, perform it. Find the critical point by solving d1. Find the critical point by solving d2. That is the first two functions. Then print the critical points. Then find the second derivative at the critical point. So you need to evaluate them, critical points. So substitute them. So you need to find derivative, second derivative with respect to x, second derivative with respect to y, and second derivative with respect to x and y. That is dou square f by dou x dou y. So q1 is equal to s1 dot, substitute the critical points, evaluate that particular value, then substitute the critical point for s2, substitute for s3, then find out the delta value, that is q1 q2 minus q3 the whole square, that is dou square f by dou x square into dou square f by dou y square minus dou square f by dou x dou y the whole square. Then we have the condition for maxima, minima, and for the test, so saddle point, that is, so delta greater than 0, q1 greater than 0, delta less than 0 is saddle point, delta greater than 0, q1 less than is 0 is maximum. So delta is equal to 0. We have to do the further test. So let me check whether this. So the minimum value is at x is equal to minus y by 2 minus 3 by 2 and x is equal to 3 minus 2y. So you get the minimum value at that particular point. Then we will go to integration. So we'll do two types of integrations. One is the numerical integration and another one is SciPy and SymPy integrals. So let me take up the first one, SymPy integral. So the SymPy integral is very simple. You need to import integrals. So in the integrals, you have integrate command. Now integrate, the more number of times you apply, you can do second order integral, that is double integral and triple integral and so on. We'll go to transforms later. Okay, so SymPy, and in SymPy we have transforms. We can do Laplace transform, Fourier transform, Mellin transform, Henkel transform, and inverse Fourier, and so on. We can also find Fourier series, binomial expansion, binomial coefficients, and Bessel expansions we can find out. So let me begin with the basic integration. So x is equal to symbol x, y is equal to symbol y, z is equal to symbol z. That's the usual command what we give. Because we are declaring three variables, so we have x, y, z as a variables. Then give one of the function as sympy dot sin x, because either I can call sin x here, sin here, that is, I can call sin here and then remove sympy, or use sympy dot exponential also. Like otherwise you can call exponential in the beginning as usual. Then suppose I give a1 is equal to integral and integrate. So you get an indefinite integral. Okay, so now communicate restore. So we need to print a1. So we need to print a1. We need to do p print because you get the answer specific. So it is 5 e power 5x sine 2x divided by 29. So we know the integral e power ax sine bx plus c is given in this way: a e power ax sine bx by a square plus b square minus b e power ax sine bx cos bx divided by a square plus b square, with the obvious result, and we get it using SymPy. Now, if you want to do limits also, you can apply. Say for example, you apply the limit as 0 1, say. Let us see what happens. Zero 1. So it has computed in place of 1, it has taken e power 5 x, it has taken 1, and in place of x it has taken 0, and it has computed it as 2 by 29 minus 2 e power 5 cos 2 divided by 29 plus 5 e power 5 sin 2 divided by 29. Now suppose we need the value, so we can give float of a1, print a1 and float of a1. Let me clear the screen first. So y1, it has computed x 0 comma 1 and float of a1. Suppose we want it to print Then yeah, you get 27.5959, which is the answer for the solution which we have. Similarly, double integral, let me show. So I have taken the function as x and y. So it is a function of x and y. Sine x plus 2y plus x cube y to the power 4. So whether it integrates, it will the function. So it has integrated x to the power 4 y to the power 5 by 20 minus sine x plus 2y by 2. Suppose we complicate the function like y square, suppose I use inside, we need to use numerical integral for that. Y square, we need to use numerical integral. Let me check that. Okay, still good, but sometimes it gives in terms of other integral values, so we need to use numerical integrals. But suppose I substitute for the value a2 comma integral y2 comma x. I substitute x minus 1 comma 1 and y I substitute 0 comma 1. Let us check this. So it is, yeah, it has computed. But suppose we need the value of that. We print this, then print float value of a2. Give clear command here. Run the program. Yeah, it does compute. So it is a, so not just linear, even complicated integrals it computes. Then we'll go to triple integral. So it is the same concept. Only thing is, there is a function z also. Function of z also. So suppose we see this. So y3 is equal to x y z plus sine x plus y plus z. Simple function I have considered. The integral is between 0, 1, 0, 1, 0, 1, 0, 1, I think. Yeah. X is 0, 1, y is 0, 1, z is 0, 1. Now I print that with the value cos 3 minus 7 8 minus 3 cos 2 plus 3 cos 1. So that if you want float value, as usual, we can use print float and we can get that. Now let us go to integration using SciPy. So this was SymPy integration. We can go to SciPy integration. Afterwards, I'll come back to transforms. So SciPy integration. So here you can give the function actually. So all the three integrals can be performed. So my main idea is to show what quadratures it uses. So here it uses Gaussian quadrature. So quad is Gaussian quadrature. Then double integral DBL quad, and similarly triple integral is TPL quad. Then you have Romberg integration. Also trapezoidal and Simpson also can be performed. So let us check for the functions. Now suppose you have not written the function. You have not written the function like here, like how we define. Suppose we have not written it like this. Then what happens is every time you need call lambda, and lambda is a function of x defined by. So this E2 tells that it is you are defining the function of x as x cube and you are integrating between 0 to 2. Okay. So I'm just printing it directly. X cube, we know between 0 to 2 it will be 1 by 4. So F5 if I do, Okay, x to the power 4 by 4, 0 to 2. So 2 to the power 4 by 4 gives you 4. That is our result which is displayed here. Similarly, any other function cos x cube, cos x cube is 0.85547, and the error is the first one is 10 to the power minus 14, and here it is 10 to the power minus 10. So similarly, you can give double quadrature, the function of x and y represented as y comma x. So here you need to represent it as y comma x. You can represent it as x comma y, provided you give the limits in the opposite way. So here y comma x is equal to x square y square, and x ranges between 0 to 2, and the function y is equal to root x to x square I have given. So if you give x comma y, then instead of lambda x, you have to give lambda y, root y, or any other function, then lambda y, x, y square, or any other function. So here you get, yeah, here you get the value 17.28685. You can verify, integrate, do the double integral of x square y square, and you will see the value 17.28685. And approximately the error is 10 of the order 10 to the power minus 10. The other way of giving the function, I have done it for triple integral. Another way of giving the function is of this form. So that makes it simple. So you define a function. Say I have defined the function sin x plus y plus z. f1 of x comma y is the limit. The first limit where z is equal to f1 of x comma y to f2 of x comma y, and x is equal to g of y and h of y. You can change the limits, and y ranges between 10 to 12. Okay, that's what I have given. Y ranges between 10 to 12. If you see this, you can give any other limit also. Here you get, yeah, so it is computing. It has told some error because 10 to the power 10 and 12 are there. So I'll read the 0 or 1 and 2 I guess, because in case if 0 comes. In order to truncate the computation, we know yesterday we had seen, we need to click on this. So the keyboard interruption is done. Then you clear the screen. So then you start giving the command again. So it is computing. So you can either define the function externally like this, or give the lambda internally and then create the function. So either way you can do. So the value is 1.7999, and that is an integral value. Then the error is for the first one is 0.4347 into 10 to the power minus 8, and 2.102 into 10 to the power minus 6. Need to check it out, that part. I'm not very sure of that, but I think that's what it is. Then Romberg integration. Trapezoid Romberg. There are two ways of giving the integral, either through the data, and you can tell head size, step size as 0.05. You're refining. That's what Romberg integration does. Once you have the integral between values, then you refine the data by taking the smaller step size and then do the integration. So here g I have taken, g is the function y cube, and I have taken the limit 0 to 1. So you are supposed to get 0.25, and here if you refine it, what you get you can check. Okay, I'm sorry. The first one is 0.4347. I had not given Simpson's comment, so I'm very sorry. The solution for the triple integral is 0.43470838, and the error for that is 10 to the power minus 8. The Simpson solution was given as 1.799998. So I had not commented it. So because of that, the solution has come out. So Romberg will do one by one. The first one is D 0, 1. So obviously 1 by 4. Yeah, 0.25 expected result. Then the next one is, I have given only 3 points. You can give more points here. Get the solution. Maybe I'll increase it to 5. 0.4, 0.5, point. Okay, let us see what's 1 plus. Okay, sorry. 345 0.3, 0.4, 0.5. Yeah, non-negative power of 2. So we'll do only these 3 points, 0.1, 0.2, 2 power 0, 2 power 1 into 10 to the power minus 1 and so on. So if the answer is 0.01, 0.00002 or 0.01 is answer. So you replace dx by 0.1 instead of 0.01. The default one is 0.1. You get 0.02. Okay. Similarly, trap set can be taken. You know the value of function of the integral of trap set. Suppose the array is given to you 0, 0.1, 0.2, 0.3, 0.5, 0.7, 0.9. Some array I have given, and dx is equal to 1 instead of 1. We'll take it as, okay, we can take it as 1 and it is for 3 values you get the value easily because it is y of a plus y of b divided by y of a plus y of b into h plus divided by 2 plus h into h by 2 into 2 times y of c. So that's what it is. So here instead of y of c, it will be y of c plus y of d plus y of e and so on. So let us check what we get. 2.25, you can verify this integral. The function is given as 0, 0.1, 0.2, 0.3, 0.5, 0.7, 0.9. And dx is 0.1, 1. And if you give it as 0.1, then the step size increases. Only the value will decrease. 0.225. 0.225 is the solution. And finally, the Simpson's rule. We know that Simpson's 1/3 is better convergent than Simpson's 3/8. So I think here it is Simpson's 1/3 which is used. So 1.799998, which was the previous solution which we saw. So let us go back to transforms. So I wanted to show this integral transform again. So here we call simpy and simpy dot transforms, or again you can import simpy. From simpy import transforms, and from transforms you can import Laplace transform and then call the function. Laplace transform, Fourier transform, Mellin transform, Hankel transform, and inverse Laplace transform and so on. So we comment on this. Okay. So I need to repeat the integral explanation. So there are 3 quadratures which I am discussing. The first one is a simple integral. Then the second one is a double integral, and the third one is triple integral. Now we saw here, instead of function defining it in this way, we call it as f of x is equal to x cube, or f of x is equal to cos x cube, and then integrate it between 0 to 2. Or even if you don't write this, it will print it. It will give, no, here the quadrature is numerical, so it has to give the limit has to be given 0 to 2. It will print, and either lambda x or yx or y xyz you can give, or you can give the function in this way and then compute this. Now trapezoidal rule, and Simpson's rule we know, and Romberg integration is the refinement of trapezoidal or Simpson's, whichever we are considering. So Romberg, as it only told, as the Python itself told, we need to give the intervals in terms of powers of 2. So here we have 0. 0.1 is into 2 to the power 0. 0.1 into 2. If you want to give the next one, it will be 0.1 into 2 square. So that is 0.4. Let us check whether it works for this. The first one is simple Romberg integration. The second one is the interval. So Romberg B0, 1. Number of samples must be 1 plus A, and number of samples must be 1 plus a non-negative power of 2. Non-negative power of 2. So I took 1 plus 2 square. 1 plus 2 square will be 5. So to the 1 plus 2 square. So I have taken only this much. Let me top at this and show you the value for this. But Romberg here, you get the usual integration. So you get 0.25 and 0.02004. And here I told trapezoidal rule, it is h by 2 into y of 1 plus y of n plus 2 times y of 2 plus y of 3 plus y of 4 plus y of 5 plus etc. y of n minus 1. So you can check the computation, it will give the same thing. We can write the code for that. It is the same. If you have the values of this form, then you can write the code easily, or you have a trap set command here. The trap set command is there also in Octave. The trap set command is also there in Scilab also, which we'll be discussing tomorrow. So this gives 0.225. Then I was telling Simpson's 1/3 is better than 3/8. Okay, because if you see 3/8, then the interval, the step size, the space between the intervals is divided 3 times between 1. So that means it is 3 by 9. So 9 values are divided between 3 successive intervals, whereas here 8 values are divided. So 3 by 9 is much smaller than 3 by 8. So 1 by 3rd, Simpson's 1/3 is much accurate than 3 by 8. So therefore, I think it uses Simpson's 1/3 in this. That's what I told. And this is just for your information, or whether you'll be knowing these things anyhow. Okay, you get 1.79998. Then you have here SymPy I discussed in the beginning. Then we'll go to transform. So Laplace transform of e power minus 5x. I think it should be 1 by s plus 5. 1 by s plus 5, that's what we need to get. So let us check whether we get 1 by s plus 5 here. So print Q1 I have here. 1, 5. Yeah, 1 by y plus 5, because y instead of s I have given it as y here, x comma y. So it will give 1 plus y plus 5, 1 by y plus 5. You can give any Laplace transform function there, provided it is convergent and it is evaluated. It can be evaluated, or it should be exponentially convergent, or mod of e power minus sx f of x should be less than some capital M. We know that. So whenever we choose the function, we have to choose it in such a way that it satisfies that. Now here I have x bar z. So z doesn't. So x bar n z it computes, because we know x bar n is Laplace transform of x bar n is uh, n factorial divided by s bar n plus 1. So we need to get it as n factorial divided by y bar n plus 1. Instead of factorial, I think it gives gamma value. So wait, yeah, as I told, it is y power z plus 1, 1 by y power z plus 1, gamma of z plus 1, 0, real part of z is greater than minus 1. That's a condition for conversion. No, this is over. The next one is Fourier transform. Fourier transform of e power minus x square. So this is the standard function which was taken from the internet. Any other function we can try, but I think we'll get the solution for this. Yeah, root pi minus e power pi square y square. Then similarly, Mellin transform. So pi power minus y, gamma of y, limit is 0 to infinity, and Henkel transform. I think it will take some time to compute that, but let me check. Yeah, it will take some time to compute because we know Henkel transform is in terms of Bessel's function. So yeah, so you get the value of this form. Because I've given pretty print, it prints in this way. Otherwise, you can get it in the simple form also. Then we can see inverse transforms. Inverse Laplace transform of x divided by x plus 5 whole square plus 25. So we need to get it as e power minus 5x cos e power minus 5y cos y. We are supposed to get the whole square is there. So let me check what we get for this one. Okay. Yeah, as I told, because it is integrating, because the function I've given it as whole square here. Yeah, whole square, so it will integrate. It will integrate and then give the value. So it is given in this form. Theta is a Heaviside function. Theta is a Heaviside function. Inverse Fourier transform of 1 by x square plus 5. So let us check that. Yeah, you have the solution for that. Then inverse Mellin transform, again Heaviside in terms of Heaviside function. Doesn't compute because I think it is complicated even for that. Similarly, we can find cosine transform, sine transform, and inverse cosine and inverse sine transform. Cosine transform of e power minus 5x is 5 root 2 divided by root pi y square plus 25. Sine transform root 2 divided by, so then you have inverse sine transform. We're getting the same. Only the sign changes, obviously, because Fourier series is Fourier transform is one sign reversal of the Fourier inverse transform. So the same thing happens with sine and cosine. So Q1 is inverse cosine transform. 1 by x power 5, it doesn't know. So if we give it as e power x minus 5, sin pi dot exponential of x minus 5, it should compute whole square, I think it will. Takes time. Yeah, but it gives the value. Suppose we want to find the Fourier series. Fourier series of x square in the limit 0 to pi. Q2 here. So you get cos 2x, cos 4x by 4 plus. So you know that x square is an even function. So it has only cosine transforms. It has only the cos part of the series. So it is telling cos 2x plus cos 4x by 4 plus pi square by 3 plus etc. Then similarly, binomial function can be, binomial coefficient can be evaluated using SimPy. We saw factorial evaluated in SimPy. So binomial of 6, 6 is 1. So that's very simple, which I have taken. Let me show you that. It gives 1. So till now we have discussed about differentiation, integration and transforms and Fourier series. So let's go to ordinary differential equation and partial differential equation. So screen. So we have ordinary differential equation if 1. Yeah. So here I have imported sign and symbol D solve, the solver of the differential equation, the functions e power exponential function, then derivative to write the differentiation of the function, equation, there's a syntax for equation to be solved, and function to declare the function, and print. Obviously, we always use print and cos. So x is equal to symbol of x, s is equal to symbol of s, y is equal to function of y. This is the usual declaration. Then we derive y1 first derivative, y2 second derivative, y3 third derivative. Then call the function that is equal to d solve. Equation is y2 minus 6y1 plus 9y of x minus cos 2x comma y of x. So you are integrating, you are solving the differential equation with respect to y of x. Let us see the paper what we get. We can solve different equations, maybe simple equations we can take and then solve them. So this is a constant coefficient homogeneous, non-homogeneous equation. So we can you see y double dash plus minus 6y dash plus 9y is equal to cos 2x. So it is in terms of CF plus PI. So CF we will get some real and distinct, and PI will be 1 by d square minus 6d plus 9 of minus cos of cos 2x. So let us check what's it. Yes. So C1 plus C2x e power 3x minus 12 sin 2x by 169 plus 5 cos 2x by 169. The next one is Laplace transform. We'll just eliminate that. I just did it for x e power 2x. So now suppose cos 2x is not there, then only CF part, the homogeneous part has to be evaluated. We can classify also. We can classify the. We can classify the differential equations using classified differential equations. So suppose this is only the CF part should come. I just want to show that this is possible. Yes. But why this is coming? Evaluate. Equation is common. Okay, you should be careful with the brackets. equation closes there and you need to desolve it with respect to this. Yeah. So now the value will be C1 plus C2x e power 3x. Yeah. C1 plus C2x e power 3x. Please remember, don't do the mistake what I did, please. So equation should be given together and comma y of x to solve with respect to the derivative. So desolve y of x. Then this is another equation. This is a third order equation. Y3 plus yx minus sin x. So this is dq plus 1 of y is equal to sin x. Obviously, this will be d plus 1 into d square minus d plus 1. So you get a real and irrational and distinct root. So let's see. Now you get a real and imaginary. So you get a complex conjugate. So complex conjugate is given by C1 sin root 3 by x, 3x by 2 plus C2 cos root 3x by 2 into root x. Then the pi part. This is the pi part. Sin x by 2 plus cos x by 2. So all the linear differential equations can be solved easily by sin pi. You just have to give the equation and then solve it with respect to that. Now we solved second order, third order. If you give fourth order, you can solve the fourth order equation also. Let me give one example of that. Y4 plus y of x. Okay, that's all I'll give. So instead of y3, I'll compute y4 and I will write y2 comma x comma x. So we can do it like this. So it is a fourth order derivative. So get y of x is equal to c1 sine root 2 x by 2 plus c2 cos root 2 x by 2 divided by e power root 2x, root of e power root 2x plus the remaining terms plus sin x by 2, which is the pi part of it. Okay. Now whether we can solve Cauchy-Euler equation, that is what the main discussion will be now. So we'll give x to the power 4 equation, x to the power 4. So we give some x to the power 4 here. R y to the power 4 plus x square r y2 of x y2 plus, because I'm not given y3, I'm not giving that, or minus, we can give minus y of x minus y of x xy1 we can give, in fact x star y1 of y1 minus y of x minus sin x, or e power x we can give, minus exponential of x, solve it for y of x, print z. Okay, let us check whether it is solvable. Take time, but I think it will compute. We can solve Cauchy-Euler also because it is reducible to linear equation. So only thing is it will take time to solve it. We can open other files. So apart from ordinary differential equation, I thought I'll discuss partial differential equation also. There are other examples. Ordinary differential equation can also be given in a different form. So ODE2, ODE1. So here you see, instead of giving G is equal to D solve derivative of f of x xx comma 9. So it is D square plus 9. So D plus 3, D square plus 3i root, D square plus 3i into D square minus 3i. Okay. So the solution is plus or minus 3i. The complementary auxiliary equation solution would be plus or minus 3i. So the complementary function would be c1 cos 3x plus c2 sin 3x. Let us check that solution immediately after we get the solution for Cauchy-Euler. There is Cauchy-Euler here too. There are some equations, but and open the other files also so that two four and partial differentiation. Yeah, so this is this is another way of giving the function. So let me explain that once we finish this problem. Here we have given it in the same way. So this is we close OD4. This is not required. This dot we shouldn't give. This is wrong way of giving. So anyhow, I'll not explain it. Okay. Then the partial differential equation examples are there here. And again here also we have this dot which I think it is taking a lot of time. So I'll truncate this. I'll give a simpler problem and then I'll conclude the ordinary differential equation. I'll show the other way of declaring the syntax, but this is the most easiest way of writing the function in the Python. So I'll close this. I'll give a simpler function. X square will give. In fact, x square we can give. 5 to the power 4 we need not do. X square y square minus 2xy1 we can give 2 star xy1 2 star xy1 minus y of x, or here it will be plus y of x minus exponential of x y of x. So let us see whether this works. It should work. It should be rather easy for this to do. GitHub.com. Appreciated. Okay, that is fine. It's just a warning, depreciation warning, but it should compute. Okay. The other way of declaring the function is given here. So f of x dot derivative 4 times 2 times f of x dot derivative 30. So that means this is d square f by d to the power 4 f by dx power 4 into 2 times d cube f by dx cube into 2 times d square f by dx square minus 6 times df by dx plus 5 times df by dx. So you are giving d solve of that, and then nth linear constant coefficient homogeneous. So that's the classification what it is giving. So you need to specify that classification in order for that to solve the differential equation. Or we don't have to do that exactly. We need to just give f of x. We give the classification. We know that with the classification. I just comment this. I'm sorry, really, this is taking a lot of time, but it computes it. You can do the Cauchy-Euler equation also. I'll truncate this and run this. So here you got the solution. C1 plus C2x e power x plus this one. So instead of x, suppose we write x to the power. Okay, I'm not writing x to the power 4, x2 x. and x to the power 5 will take. We solve square square f of x p square plus 6 star x star f of x plus 5 f of x. So I should solve this particular problem. Yeah. So as I told you, got the solution as C1 x to the power 7 by 2 minus root 29 by 2 plus C2 x to the power root 29 by 2 plus 7 by 2. This is a simple example of Cauchy-Euler equation. So we could solve Cauchy-Euler equation also using this. Then the other representation of the same function. You can check some more documentation of SymPy, NumPy, and SciPy, wherein you will get the classification also done. You can do classification of PDE, you can do classification of ODEs. Only the linear equations can be solved. For non-linear, you need to do the Runge-Kutta or Euler modified and so on. We'll go to that in a moment. Before that, we'll do PD solver. So there are two ways of declaring the function. Again, function f of x f of z is equal to function of z. So z is equal to x comma y you can give, or you can declare it as z x y is equal to map function z x y, so that you can separate it using addition or multiplication. That's what it is given. But not do that. We'll do the first one. So here, if we give p print classify underscore PD z1, so it will classify the derivative differential equation, partial differential equation. So derivative with respect to x. So it's a Lagrange equation which I have given. So Pt plus Q is equal to R. So that is where capital P is 6xy, capital Q is 9xy x square, and P is dou z by dou x, Q is dou z by dou y. So let us solve this. So this is the equation. So you have the solution as f of minus 3x square by 4 plus y. So this is a first order linear variable coefficient. The next one was second order equation, dou square z by dou x square plus 6 into 6 plus dou square z by dou y square equal to 0. That was the equation which I gave, but I'm afraid it is not solving this. I can show that it is not solving this. It's not solving in the sense it takes a lot of time. That is a disadvantage of my computer. Yeah. So from 79 it has gone to 1. That means it has gone to a different routine. So I think it will take some more time because the red button is still on here. Red color is still on there. So that means it will take time to compute. But we'll go to Runge-Kutta now. So till now what we have discussed? We have discussed continuity, we have discussed limit, we have discussed differentiation, we discussed integration, double integral, triple integral, integral transforms, ordinary differential equation solution using SymPy, partial differential equation, only the linear first order partial differential equation, the second order and higher order it is difficult for it to solve, but you need to write a numerical routine to do that. You can definitely do that part. So if you have a heat equation or a wave equation or a Laplace equation, you can write a numerical routine in terms of finite differences or finite elements and so on, and then you can get the solution. But I'll show only one example of solving the differential equation of the form dy by dx is equal to f of x comma y, and y is equal to y naught as the initial condition. So we'll go to Runge-Kutta problems or Euler modified first. So as I told, it is still computing. So Euler modified. Euler modified is. So it is very simple. Predictor is y naught plus h f of x naught y naught, we know that. And corrector is y naught plus h by 2 f of x naught plus x1 comma predicted value of y. So I'll close this because I think it is taking a lot of time. I'll run this particular thing. So yeah, even after closing. Okay. I think it has truncated the routine and then it has gone to a new console. Probably because of some error internally. So I'll look into that, but I think it doesn't compute the higher order partial differential equations. In my experience, at least we need to write a numerical routine for that. So Euler modified, the equation which I have taken is e power x plus y divided by 1 plus e power x plus y. 1 lakh computation. So you don't have to give so huge, but it will compute. And give it only. So Euler x naught y naught here. Euler x naught is 0, y naught is 1, and I want to compute it for 0.1. That's all. 1.731, that is a predicted value. 1.0747 is the corrected value. So you can play with this. You can increase the function also. You can write f of x is equal to e power x plus y by 1 plus e power x plus y, or give a matrix here or an array here. Sorry, you can give an array as Patra sir had done in the first day. He had a set of 3 equations in the beginning, which was a toy model, where he used Runge-Kutta 4m. I'll be doing Runge-Kutta 4m for 1 equation. Then he extended it to 7 equations, and then he extended it to up to 10 equations, I think. So you can do that. And it is known that we can do that because that's what we teach in engineering classes also. For 2 equations, we do that. So let me finally go to Runge-Kutta 4th order. Okay, so the formula we know k1 plus 2k2 plus 2k3 plus k4 divided by 6. Y1 is equal to y naught plus k. The same function, the convergence would be much better. The error would be much lesser than the previous one. So k4m, the same value I'll take. Yeah, so once you compute this, rk4m 0, 1, 0.1. So the value was 1.04967178940560. So any other function you can try. I think today's session I'll end here. Tomorrow we take up. I think I can do graph theory tomorrow and also discuss some other FOSS like octave maxima, especially because on the second day I thought I got a question like Mathematica and Maple are much better, but in free softwares you have Mathematica, sorry, not Mathematica, the Maxima, which was like symbolic toolbox, and Python is obviously much better than any other thing in terms of free softwares. So let me discuss Maxima on that day, and Octave is a replica of MATLAB, so we'll discuss about Octave and we'll discuss about Scilab. So I'm open to questions now. I think I can stop this presentation now.
Thank you, Balkar sir.
Thank you, ma'am.
Sir, one question is there from Sushma ma'am. How to create forward, backward and divided difference table in Python?
Yeah, table you want to create. So that is a bit difficult challenge, which we also faced, because yesterday, if you see, I just gave forward difference calculations, but table I didn't create and show it to you. But you can give print statement and give tab /t/n. Usual C programming what you do, the same thing you have to give. /t in print and /n for tab /t and /n for the next line. So once you do that, you get the table there, and you need to put it in the 2 for loops which are there in the program which I showed you yesterday. Yes.
Sir, thank you, sir. One more question.
Yes,
Can we use Python to convert PDE to ODE by the method similarity transformation and to solve ODE by coupled equations?
there is a command in Python called as PDE underscore separate underscore mul, where the multiplication will transform. So I have given z is equal to a map of function zxt, where z can be transformed as x of t and y of x of x and y of y. Instead of zxt, I have given zxy. Z is equal to x of x into y of y. So that transformation it will give. And then you will have to take those values and try to solve for the next level. So that part it does. Yes.
Okay, sir. Thank you. Thank you for the answers.
Yes. Can we solve any type of mathematical problem? As I told you, there was one question, sir. I just answered that. There was one question. One person had asked, "Can we solve any sort of mathematical problem?" Yes, because we have numerical routine, we have symbolic routine, and scientific routine. So any problem can be solved using Python. Any problem can be solved using Python.
Okay, sir. Thank you so much, sir.
Yes, sir. Thank you, sir.
Thank you. Within a short span of time, we could able to see so many very important mathematic topics, especially some topics like transformations, double, triple integrals, which are highly time consuming and also complicated ones. We could able to solve in a very short span of time and very easily also, provided we know the syntax, the certain commands.
Yeah.
Within the given time, you could able to do your best. We have given a good overview of that, but still we are missing a feel of practical learning, practical practicing, etc. Now it's up to us to work on the foundation given by you. We try to develop that to the further levels. Thank you so much, sir, exploring us to variety of things in the Python, which is related to mathematics. Thank you. We'll continue with tomorrow's session. Thank you so much, sir. Thank you.
Thank you, sir. Thank you.
Thank you, participants. So we'll end our session today. We'll continue with tomorrow's session by 10 a.m. Feedbacks will be shared to WhatsApp group also. Try to finish it up. Thank you.